In this video we're going to use the Miller effect to make an equivalent circuit for the common emitter amplifier and see if that'll simplify our bandwidth calculation. I've copied our model for the dynamic common emitter here, and we're going to see if we can make it simpler using the Miller approximation. To do that we're going to go over a few simple facts. First, we recall that our gain is minus GM times RC parallel RO, but we can also recall that our definition of AV is that it's the ratio of changes in the output, or VC, to changes in the input, or VB. So that's the same as having like our Miller effect triangle attached from VB to VC. VC is gained up by some amount relative to VB. And that means that C mu is in feedback across that amplification. All of these other components are acting like the funny triangle, and C mu is in feedback because it directly connects VB to VC. So we're going to try to find a Miller representation for C mu and then attach that to ground, so to take the Miller approximation for this circuit. Doing so gives us this schematic where CF, instead of being a C mu connected across here, is instead a Millerized C mu attached to ground. And this is just the Miller equation. Right, we have 1 plus the gain, and we're adding it because the gain here is negative. I've copied our simplified schematic from the previous page to see if we can find the transfer function more easily. And it turns out we can. That's because our output voltage is given by the usual GM times some resistance. And all of our capacitance is just in parallel to the input, which means that we're going to have our base voltage roll off like a first order system as the frequency increases. So the dynamic term in the middle of the page is describing the change in our base voltage. This third term is a little bit weird, but it's just capturing the conversion of our input current source back into an input voltage source. And it winds up turning into a simple voltage divider between the source impedance and the input impedance. So we can estimate the bandwidth pretty easily with this approximation because we're just pretending this is a first order system. So we're going to have one pole and it's going to be located at 1 over this time constant. And pulling that out looks like this. Notice that the Millerized C mu appears pretty prominently in our equation. We can compare this against the full function that we derived earlier. I've pulled out the tau1 value down here and written it down for comparison, so that we can check it against this tau1 value, against our first pole in the Miller approximation. When we do that comparison, we see some big differences. First, we've clearly lost some nuance because we don't have our feed-forward 0, right? This is replaced with 1. And we don't have our second pole. That's gone away. Maybe that's fine. The feed-forward 0 is at this really small value, sort of GM over C mu is a small number. And we were assuming the first pole dominated our transfer function anyway, that tau1 was much larger than tau2. However, we also lost a term in our estimate of tau1, like this C mu RC parallel RO doesn't appear up here. Which means our Miller approximation is going to have a slightly smaller time constant than our real approximation, or than our real expression. And none of these are great behaviors for an approximation. Losing the second pole and the 0 can affect our stability. And if we're estimating bandwidth, then we prefer to have a conservative underestimate to an overestimate. So the Miller approximation is not conservative and it loses a lot of nuance, but it's super quick and it gives us an easy way to estimate the effect of feedback capacitances. So it's good to have around in order to build physical intuition for what's dominating the time constants of your circuit. So in summary, C mu gets Millerized in a common emitter amplifier. The Miller approximation pretends that the input cap, which is just C pi and a Millerized C mu, determines the whole transfer function, and that makes it first order. So we lose the zero in the second pole. So this is not a conservative approximation, but it's good because it's simple and gives physical insight.